In this part of the lesson we shall develop what is known as the dihedral angle, where the two inclined surfaces meet at the outside corner of the legs of the saw stool. Then we will develop the true shape of the edge and side of those same legs. So let's look at this dihedral angle from a different perspective. Imagine if instead of legs all around it was sheet material, like a hopper head inverted or a hipped roof or a canopy, all shown here in pink. If we put a bevel across the hip line between those two pitched surfaces, the angle would be greater than 90 degrees. We would get the angle for the ridge capping if it were a hip roof, for example. In other words, in this case, a hip ridge capping angle equals dihedral angle. Here we have a triangular plane springing from the horizontal or floor plane, coming square onto the hip line or outer corner of the leg. You can see here that the tip of the isosceles triangle has to rise from the floor plane so as to cut square across the inclined leg. So even though the two surfaces of the leg make a 90-degree angle on the floor plane, the angle will be greater than that where this triangular plane cuts the leg. Because this inclined triangular plane cuts the leg at 90 degrees, it will give us the true sectional view and dihedral angle for this leg, shaded in green here. This is the view of the triangular plane swung down onto the horizontal plane, which is the floor plane. It's only when we swing this triangular plane onto this horizontal or floor plane that we shall see the dihedral angle later on our setting out sheet. This is an animation of the triangular plane pivoting down onto the horizontal plane or floor plane on two legs. Note the base of the triangular plane cuts square across the plan view of the hip line, shown in red. This relationship can happen anywhere along the plan of the hip line. For example, the nearest triangular plane here rotates up from the end of the hip line, while the other example rotates up from a junction about a third of the way along the hip line, you'll notice. Both examples will cut the leg at 90 degrees, and so both will give the same angle even though they have sprung from different points on the hip line at floor level. So the vertex nearest the leg on the green shaded triangle is the dihedral angle. So to get the dihedral angle, we will work off the orthographic view shown here on our setting out sheet. For clarity, I shall omit some of the lines shown here. So to start, we will use the rise distance from floor plane to the underside of the saw stool and draw that distance square off the hip line on plan as animated here now. The longest line, the hypotenuse, in other words, on this shaded right angle triangle is the true length of the hip line, by the way. So I guess you could say the first step to getting your dihedral angle is finding the true length of the hip line. So next, where the junction between the hip line on plan meets the rise line, draw a perpendicular line from there onto the true length line of the hip, as shown here with the frame and square. So we'll zoom in here so we can see a bit better detail. So the next step is to swing that perpendicular line down onto the plan line of the hip as shown here now. So if you cast your mind back to when we introduced the um, triangular plane that cut the leg at 90 degrees, that's basically what has happened here. And the white arrow tipped line arc there has now brought that triangle down onto the horizontal plane effectively. And so here we have that triangular plane that's shaded in green is now on the floor plane. So now we can see the true angle, which is the dihedral angle for this corner of the leg. So as I introduced the dihedral angle earlier on with an isometric view, and I gave a smaller example of that green shaded triangle, I'm doing the same here just to show you that you can pick anywhere along the plan line of the hip and it'll still deliver the same angle if you follow the same procedure. And once we have that triangular plane on the horizontal plane and we can see the actual dihedral angle, we can take the parallelogram, which is the sectional view now of our leg when the dihedral angle is planed onto that leg. And notice here that it's the outer corner of the leg must be the corner that's more than 90 degrees. Remember that when you're making the saw stool. It's a very common mistake that the corner that's less than 90 degrees is kept on the outside corner, and that would be a mistake. This here is an example illustrating that half the dihedral angle would form the mitre angle between the end and side of a canopy or a hopper shape, if that's what you're developing instead of what we're doing in this case, which is a saw stool. But I wanted you to see the relationship across into other areas of carpentry joinery. And as mentioned earlier, if this was a hipped roof, well, what I've shown there is the section through the ridge capping. If this happened to be a hipped roof, that would be the ridge capping for this particular hip, if it were a roof. Okay. Next, we will focus on discovering the true shape of the legs of the sawhorse. From this true shape, we will get the true length and true angles for each leg. This means that we can then mark the actual leg and transfer those marks directly off the setting out sheet onto the actual leg. So let's look at the true shape development from a different perspective. Imagine if instead of legs all round it was sheet material like a hopper inverted or a hipped roof or a canopy, all shown here in pink. You know, what you see here in pink could be a hip roof, it could be a canopy, it could be a hopper. If we swing those surfaces onto a vertical plane, we would get the true shapes and therefore the true angles for those surfaces as well. After that, we take out the leg surfaces from those overall surface areas. So here we can see the end surface has opened up to the vertical plane. And here we now have both inclined surfaces swung up onto the vertical plane. So I hope this isometric view has given you a visual on how we're going to proceed now to develop these surfaces when we go to our setting out sheet. This is the end surface shaded in pink. It's currently pitched away from you. So this is not the true shape you see here. Therefore, we cannot get a true length or true angle from this shape. If we can determine the distance from the floor plane to the underside of the sawhorse, where this inclined pink plane ends, then we will be able to get the true shape. So currently we have a an arrow tipped black line drawn here comes square off the floor plane, uh, but it's angled away from us, so we actually can't see the true length of that line drawn on that surface either. But due to the side surface pitching in at the same angle, we can see the true length of this arrow tipped line from the perspective shown in red. The following is an isometric view making the same point. Here is an image to illustrate that our viewpoint is not seeing the true length of the black line, as it's not being viewed square on, as it were, from the in view. So therefore, it's not the true length. On the other hand, here is an animation to illustrate that our viewpoint is seeing the true length of the red line, as it's viewed square on from the in view. Should it be the case that if both surfaces are of a different pitch, then we would have to view the true distance between the baselines from the elevation perspective as shown here. So now we know that the distance between the floor baseline and upper baseline will increase by the distance illustrated in red here. And we also know that as the floor baseline is the pivot line, when this trapezoid is opened up onto the vertical plane, the upper line will always move away from the pivot line at an angle of 90 degrees. This point is worth remembering for future developments. Once you establish what the pivot line is, you know that everything will move away from that line and it will move away at 90 degrees. So here the trapezoid shape is stretched by the red distance to show its true shape now that it's opened up onto the vertical plane. Here the true shape of the edge of the leg is developed to include the tenon in a similar manner as we just saw with the end shape being developed. Then develop the tenon from its in view onto the true shape as animated here. So now we can mark our leg directly off this true shape on the setting out sheet. We now have the true lengths and bevels for this leg's edge. And here we shall develop the side of the leg true to the top of the sawhorse using the same approach as we did when developing the edge of the leg. Note the steps animated here. Now we can transfer the true length and angles directly off this setting out sheet onto the leg itself, but make sure the dihedral angles are already planed on the leg. So that is the end of part 2 of this animated lesson. The next and last part of this lesson will take us through the jointing and assembly to include a tray on this saw stool. In the meantime, you can have the 4 legs ready with the dihedral angle already planed on, and you can chop them at 25 inches long for now. That will leave you enough waste, and of course you can have the top machined up to its size, and you can have it chopped off at 800mm long. Okay.